this way, now based on control, this Z would be equal to one of the inputs, or in other words, we can say that it is sending one of the, it is selecting one of the input and copying it to the output. Okay, so other things, the number of inputs could be as many as possible. It can be minimum, it could be 2, and it could be as many as anything. Okay, and if I need to design this particular multiplexer, then this is the typical Boolean equation, or Boolean equation for this 2:1 multiplexer. I would say that C bar means invert of C, and it is ended with I0, plus means OR operator, and then C is ended with I1. So if we see the sum, or if we make this whole circuit, so here whatever is the value of I0, that would be, the Z would be equal to whatever is the value of I0 if C is 0, else it would be equal to I1. Similarly, if I need to design 4:1 multiplexer, the number of input in control would be 2. So let's say A and B are the control inputs, and then I can say Z is equal to A bar B bar I0 plus A bar B I1 plus A B bar I2 plus A B I3. So in this way, we can keep on designing any bigger multiplexer. So here in this lecture, focus is not on designing multiplexer, but we want to see how these multiplexers can be utilized. Okay, so now before going to that, at least a couple of things we have to understand is that if the multiplexer has 2n inputs, then the number of control lines required would be n. So let's say if the number of inputs in my multiplexer is 8, then I would require 3 control lines. Similarly, if the number of inputs are 16, the number of control lines I would require is 4. Okay, and typically if I want to go and design a bigger multiplexer like 1024:1, then you don't create one big multiplexer that has 1024 inputs. Instead, what we do is we break this multiplexer into smaller one, like 4:1 or 8:1, and then keep on hierarchically designing it. Okay, and one more related circuit which is also quite important, that sometimes these multiplexers by default are said that it's multiple bit multiplexers. For example, 4-bit 2:1 multiplexer or 8-bit 2:1 4:1 multiplexer. So if I want to design this 4-bit 2:1 multiplexer, it would be pictorially represented something like this. Here, my input I0 will be 4 bits. Similarly, I1 is also 4 bit, and based on control, one of this I0 or I1, these 4 bits would be sent here or copied to Z. Or in other words, 4 bits of Z would be equal to 4 bits of I0 if C is 0. If C is 1, then 4 bits of Z would be equal to 4 bits of I1. Okay, so then we would, with this background, let us see how we can use this multiplexer in different applications. So first and most important application of this multiplexer is this multiplexer can be used to design any generic circuit. Any generic circuit means, let's say if it is a 4:1 multiplexer, then you can design any 2-input circuit. So we have to understand that there is a possibility of overall 2⁴ number of possibilities of these functions. So for example, with this 2-input, we can create something like 16 functions. So all those 16 functions, any one of those 16 functions can be implemented by 4:1 multiplexer. So how do we do that? For example, this is 4:1 multiplexer. Then if I give input as 0, 0, 0, 1, okay, and then I use AB as a select line. So what would happen if AB is 0, 0, then Z would be equal to 0. If AB is 0, 1, then Z would be equal to 0. If AB is 1, 0, then Z would be equal to 0. And if AB is equal to 1, 1, then Z is equal to 1. So essentially, this is a truth table of AND gate. So in other words, I can say this Z actually represent a AND gate. Okay, so similarly, any other functions of 2 input can be designed using 4:1 multiplexer. Or similarly, if I want to design any 4 input function, I would require 16:1 multiplexer. And further, the next question also arises here, that how do I give this 0, 0, 0, 1? So will I manually ground them or will connect to VDD? One alternative is that I can use a memory element. So let's say there is a 4x1 memory. So that means depth is 4, width is 1. So this 4:1 memory is there, where on the first address 0 is stored, second address 0 is stored, third address again 0 is stored, fourth address 1 is stored. Now, if I store this 0001 into some sort of memory elements, or I can call it simple memory, and then connect all of these memory elements directly to the input of these mux, then I need not to manually connect the input to ground or manually connect input to VDD or high. So this way, this whole circuit is not only generic but also programmable. Programmable means at runtime, if I change the value, or at configuration time, if I change the value of this memory elements, then the function, whatever this mux is going to perform, would be different. And this is the precise concept used in almost all the FPGAs. So they create such kind of memory elements within the multiplexer, and when you press configuration button, all of these memory elements, or these memory elements are called lookup tables. So these lookup tables are filled with your configuration data, and this way your mux is, or your FPGA is behaving like the circuit you are configuring. Okay, I would repeat this point. So in your FPGAs, otherwise when it is brought from the market, or when it is purchased, it is blank. So essentially it does not represent any circuit. But when you design a circuit in your Verilog, synthesize it, and then do a placement routing, burn it on FPGA. So what does this burning mean? That these LUTs would be filled with the circuit which you have created in your Verilog. So that particular circuit, now these LUTs would represent those function block which has been created by synthesis of the circuit. So this way, this genericness of mux plus programmability is helping us in designing any circuit what we want. Okay, so this is one, or first most important application. The other application of multiplexer could be, it can help us in realizing if-else or switch constructs. So whenever we are giving some English specification, or whenever we are giving C, C++ kind of specification, then many a times there would be constructs like if-else conditions, or switch cases. Switch cases are also essentially if and if-else conditions. So if we have these if-else conditions, then these if-else conditions can be efficiently implemented using multiplexers. So let's take an example. Let's say we have this if-else statement, that if A equal to 0, then Z equal to 10. If A is equal to 1, Z equal to 15. And if A is equal to 2, Z equal to 0. So if I need to realize this in hardware, what I can do is I can choose A, which has value 0, 1, 2, as a control to my multiplexer, and then this I have to use 4:1 multiplexer, and in 4:1 multiplexer, A would be a 2-bit control, and my input here would be 10, 15, 0. Fourth one, let's discuss that what should be value here. So now if A is 0, then Z would be equal to 10. if A is equal to 1, Z would be equal to 15. If A is equal to 2, Z would be equal to 0. Okay, so this way, this multiplexer is a very efficient implementation, hardware implementation of if-else construct. Now, whenever we are talking about multiplexer, they are always written as 2 to the power n ratio 1 multiplexer. So here I require only 3 inputs. I doesn't require 4th input. What would happen to this 4th input, or what should I connect here? That's a very interesting question, and also worth investigating, that what should happen. So let us say I give this 4th value as something like 50. What would happen now if I know that A is never going to be 3? Then whatever I give here, it doesn't make any sense. Okay, and if you clearly know that A's value cannot be 3, then you while implementation of your circuit, you can remove that part. But if your multiplexer is a built-in component, okay, or we can sometimes we also call it off-the-shelf component, so which you are picking it from the library, then you don't have choice. You can't do anything about the third. This multiplexer would be standard 2 is to power 1, 2 is to ratio 1, or 4 is to ratio 1, or 8 is to 1. So if we have those extra inputs, what should we do? Sometimes we simply connect them to 0 so that they don't bother us. Okay, and the output is always deterministic. We know that what the output is going to be. Okay, so yeah, so this is about the 4th input, and sometime our synthesis tools are also very smart, that if they see that there is no input connected, so they will try to burn out or purge the components which are not actually required or which are not actually used. So these smartness of synthesis tool will take care of if you are not providing any particular input or any particular output. Okay, so one more question arises here, that probably instructor has created this case deliberately so simple that A is having only values 0, 1, and 2. But in realistic scenario, whenever we have this if-else statement, the conditions and the variables or the comparisons are always different. They could contain different, even multiple comparisons in the same if statement. So can this multiplexer be used for those cases also? It's a question which is worth considering and thinking, that can I use multiplexer in a generic if-else condition, whatever B is the variable, whatever is the comparison statement. Okay, so let's look at such an example. So let's say the example is something like this, which doesn't involve A is equal to 0, 1, and 2. So let's say I'm creating the same example here, that if A is less than 0, then Z equal to 10. If A is equal to 0, then Z equal to 15. If A is more than 0, then Z equal to 1. Z equal to 0. So here, can we use that? Now, it could be used, but the design of multiplexer would change slightly. Okay, so here I'm using 3:1 multiplexer, where condition, number of bits in the conditions are also 3. So it is not a regular multiplexer, but we call it one hot encoded multiplexer. So here the 3 bits of condition, only one bit be true at one time. So let's say if 0th bit is true, then that means 10 would be taken. If first bit is true, then 15 would be taken. If second bit is true, then 0 would be taken. Okay, and it would be ensured in one hot encoding that only one of the bit would be 1. Okay, and in that way it is easier to design this. For example, the condition 0th bit of condition, I can say that whenever A is less than 0, then this would become 1. If A is equal to 0, then condition first bit would be 1. If A is more than equal to 0, then second bit would be 1. So there is also, because these conditions here are actually mutually exclusive. Because they are mutually exclusive, no two conditions can be true at same time. But it is possible in some other scenario that two conditions are true at same time. So in that case, the design will become somewhat more complicated. We have to first have somewhat like priority encoder, and that priority encoder would help us in generating the correct conditional bits. So priority encoder we'll discuss in some of the later slides. So this way, this multiplexer can be used for generic construction or hardware relation of if-else construct. Extending this if-else to switch is even more easier, because in switch you can clearly find out what are the condition bits, and for each condition there is only one input here. Okay. Can there be other applications? Yes, there are many other applications. So wherever I am selecting, wherever the designer is selecting one input out of several inputs, then we'll use multiplexer. So there could be several example in a designer's life which they can see. So for example, arbiter is a component which resides in buses and controllers, which will take multiple inputs and will arbitrate that which of the inputs should be connected to the output. Okay. So similarly, there's a device hub controller. So there are many devices which are connected. Now you would like to see that which particular device should be connected to host. Bus controllers will also have similar things, that a typical bus will have many masters and many slaves. You would like to see that which particular slave should be connected to which master. And a router, network switches, they also have similar considerations, that there are multiple inputs coming and you have to send one of the input to the next output channel. So this way, this multiplexer forms one of the most important and highly utilized combinational circuit in while designing digital circuits. Okay. So the next component which we are going to discuss is demultiplexer, which is inverse of multiplexer. So here you will have one input and multiple outputs. Based on the control input, the input would be forwarded to one of the output. So for example, if we talk about, if we consider this demultiplexer as 1:4 multiplexer, then if control input is 0, then in would be copied to out 0. If control input is 1, then in would be copied to out 1, and if control input is 2, then in would be copied to out 2, so on and so forth. So this way, your input is finding a correct route, which one, where it should be sent. Okay, and like multiplexer, here also my input and output could be multiple bit wide. So it could be 4-bit wide, 8-bit wide, based on the requirement of the design. So similar to multiplexer applications, these demultiplexer is also used in almost all the scenarios wherever multiplexer is used, like in routers or in network switches or in bus arbiter, because it's a kind of a complementary function of mux. So let's say the input first it is selected to send to the same source. Now that particular source is sending the information back, so it again has to find that which particular slave the information should be sent. So I'll repeat. So let's say there are n slaves and one master. So first master slaves are sending information to master, and then master also need to send the information to slaves. So whenever master need to send information to slave, then it would be using demultiplexer, and whenever all the slaves, one of the slave has to send the information from slaves to master, then you will use multiplexer. Okay. So other interesting applications could be, it can be used as serial to parallel converter. You see, there is only one input and multiple outputs are there. So you can use it to construct serial to parallel converter. In case of serial to parallel converter, in the output you will have a latch. So as soon as, let's say, first bit is coming, it would be stored in first latch. As soon as the second bit is coming, it would be stored in the second latch. And after, let's say, it is one demux, Then after 8 bits, you have a complete register with you, and you can send that content to anywhere else. So this way, your serial to parallel encoding can be done efficiently using Demux. And small memories and register file, if you have to write data, then also Demux would be used. So you would have an address. This address would act like a controller. So this is the example I'm talking. So let's say there are 16 registers, and your 4-bit register address would act like a controller. And if you want to write data, then data input would be sent here, and then this data would be written to one of these registers. So this way, demultiplexer would be used for writing the data into register. On the other hand, as a complementary circuit, if I want to read any of these registers, then I would use multiplexer. So multiplexer would read from all these registers, and based on the register address, then we can see what data is there in that particular register. So let's look at the next circuit. The next one is the next one is also a popular one, decoder. So it's also called a line decoders. So line decoder is essentially very similar to demultiplexer, assuming my data in, assuming my in is always 1. So that means if input is always 1 and I'm sending a control, I'm sending a 3-bit control, then only one of the out would become a 1. So let's look at this decoder again. So let's say there are 3-bit control or 3 inputs. So if input is 0, 0, 0, then my y0 would become 1. Similarly, y1 will become 1 when my input is 0, 0, 1. So based on whatever is the numerical value, that particular ith output would be 1. And also it is made sure that only one of the output is high. So this way, this decoder is, there are 2 things to be understood. One, that although structurally or internally it looks very similar to demultiplexer, but it would have different utilities, different applications, and different perspective. Similarly, if I have 4 to 16 decoder, then there would be 4 inputs and there would be 16 outputs. This decoder also sometimes it is active high or active low. That is also it depends on the circumstances or scenario where it is being utilized. So when it is active high, then only one of the output will be 1. If it is active low, then only one of the output would be 0 and all rest of them would be 1. Okay, and where it is used, it is mostly used in control signal generators, control circuits. So for example, if I have 8 modules, okay, and now I know that out of these 8 modules, only one of the module has to be enabled. Okay, then there would be a 3-bit control signal, that using that 3-bit control signal, we can give it to 328 decoder, and these y0, y1, y7, all of these we can connect to each of the module enable pin of all the modules. So this way, whenever my input is 0, 0, 0, module 0 will be enabled. Whenever input is 0, 0, 1, module 1 would be enabled. So similarly, we see the observation is that this decoder, whenever we have such kind of control circuits, then decoder is very efficient here. Similarly, the other application which is also quite popular is if in your processor, when you want to do instruction encoding. So for example, you just specify a opcode, and based on opcode you will choose which operation to be performed. So this opcode is sent to your decoder, and the decoder will further connect it to the various operations, and those operations will get enabled. So decoder is again very efficient in doing instruction decoding. In memory subsystem also address decoding, we use decoders. Okay, the reverse of decoder is an encoder circuit. In encoder, you will have pushed power n inputs and n outputs, and we make sure that only one of the input is high, and whatever is the input number, that particular number would be reflected in the output. So in a standard form, this is the whatever is the input number, that number will be shared to the output, but there could be specific encoding schemes. For example, gray codes, or you may have a totally application specific encoding schemes where you have to custom design your encoders. What if multiple inputs are one at same time? Then we have to use priority encoder. So priority encoder means if multiple inputs are one at same time. So for example, again, take this. So let's say this is the reverse circuit. These are the inputs, and in the input, multiple of these are one at same time. Then which one would be encoded here? Then we have to prioritize things, and based on priority, you will decide that which particular pin would be encoded. So for example, you have interrupt systems. So multiple interrupts could be high at same time. The interrupt which has higher priority would be sent back to processor. So that ID is converting that all the interrupt pins to the interrupt ID is done using this priority encoder. So this summarizes our first part of this module, where we were discussing that how commonly used combinational circuits can be used based on scenario, based on application. Okay, so I also understand that this was pretty fast because it was a revision exercise. Now, when we look at the second module, where we are trying to attempt this bus controller program, then we'll see that how we can think that these modules, some of these commonly used modules can be used in actual design. So before I go to part 2, I will take a pause here, and if there is any question, I'll take that.